Sabe, isto não está aqui a...
Vamos começar.
Funciona, não tem que não está a passar, não é qualquer coisa que não está. Ok.
Okay, great. Yeah.
Okay, so we can start. Good afternoon, everybody. We are here to start Friday at the ISISE conference of this new season, and we are going to start with a cycle of the conference that will be performed by some professors and civil engineers invited from Spain. And that's why this cycle of conference at the beginning of this new season is designated by Good Neighbors. And for these first conferences, we invited one professor in the civil engineering, Alejandro Bernabeu. To start, I'd like to thank, of course, to come to the civil engineering department at the University of Coimbra, institution that I think is very well recognized in terms of education, in terms of research, and also in the connection with the industry. As the director of the department, and on behalf of Professor Simões da Silva, that is the director of the research unit in ISISE, I repeat, I would like to thank to come to us. I have to introduce Professor Alexandro a brief CV. So Professor Alexandro Bernabeu is civil engineering. He's an expert in structures of singular buildings with more than 20 years of experience. Currently the director of his own consultancy firm called Bernabeu Ingenieros, okay? That was founded in 2014. He has developed projects also worldwide, working in close collaboration with well-known architects. He is associate professor at the School of Architecture, Technical University at Madrid, and is author of more than 14 articles, congress papers, and conference on structural design and the relationship between structures and architecture. He has been awarded with the IABSE Prize in 2015 by the International Association for Bridge and Structural Engineering. So thank you very much for to come to us. You have, I think, 1 hour and a half, more or less, for your conference. So, more 45 just. 45. Well, I was wrongly informed. Okay, so I think you can start. You have the floor. Okay.
Okay. Thank you very much for the presentation. Boa tarde, and thank you very much for inviting me to participate in this lecture cycle about the Spanish structural engineering and for visiting the ISISE and your department here in the Universidad de Coimbra. I'm delighted to be here. And I will start this afternoon in the mood for structures with 2 artistic references and thoughts. First, the Spanish abstract artist Antoni Tapies once said he started a painting by drawing a line, by tracing a gesture. The painting was then the attempt to correct that first line. To create or to design something, it is necessary a starting point, a requirement, a challenge. And structural requirements can be considered as this starting point opportunities to develop a project. Instead of considering them as obstacles or impediments that may distort or may affect to the initial design idea, we can consider them as design opportunities to improve or to develop design. Since the 80s, artist painting Luis Gordillo takes pictures of the creative process of the painting, showing the creative process and the decisions made throughout this process. These photos that have been sometimes exhibited together with the final painting represent this way. They trace the creative process and constitute a kind of archive of lost or discarded ideas. In a context in which immediacy prevails and in which projects are required in less and less time, and developments in modeling and in construction point straightforward to the final result, I think it is important to claim for the importance of the design and construction process in itself, not only in terms of the final result, but as a process, as a journey that makes the project evolves and maturate. Starting from these ideas, I would like to present several projects in which I have had the occasion to participate, developing and designing the structure of the project, and trying to show the importance on how a structure can contribute to the development of the project, of the design. The first project is the National Museum of Science and Technology in Coruña, in the northwest of Spain, done in collaboration with architects Acebo Alonso, and it was one of the first projects in which I was involved, and it was the first time I realized a structural requirement could turn into a design opportunity. The building has a cube shape, and it's formed mainly by three elements. The facade, which is a structural facade formed by steel battened columns. The interior communication core, which is made in reinforced concrete and is located eccentrically in plan, and a set of box-like volumes that are supported both at the inner core and in the facade. Finally, the roof level that is formed by steel trusses complete the volume. In this picture, we can see the concrete core, the concrete boxes that are supported in the core and in the structural facade. And this facade, as I mentioned, was constituted by steel columns, battened steel columns that were rigid enough to support the horizontal forces, the wind horizontal forces in the transverse direction of the facade, but it required to be connected to the concrete cores to control buckling of these steel columns. In some areas, therefore, it required to introduce some bracing to this structural facade. The problem was that to introduce that bracing will make lost the continuity, the uniformity that was required, that was decided by the architects for the facade. So the solution came, instead of considering traditional X bracing that will be concentrated at one end, that will clearly show the resistance structural elements and distort this continuity of the facade. Instead of concentrating it, it was considered single diagonal elements that were distributed all through the facade. Of course, the load paths are much more complex because they have to move from one diagonal to the next, but in terms of the structural behavior is similar, and it gives an image that maintains this uniformity of the facade and somehow represents like quite singular elements in both from the interior and from the exterior that actually didn't get the appearance. We don't know when you show it if they are structural elements or if they take part of the composition of the facade. So it was somehow transforming this structural requirement into a design opportunity for making more complex and even more interesting the composition of the facade. Also, in the roof level that was initially formed by Warren-like triangulated steel frames, it was then decided to divide these frames in these triangulated frames in two levels, disposing the diagonals either on the upper level or on the lower level. In a similar process of disarrangement or of bracing. And the result makes that each truss can have a different configuration, increasing the complexity and the surprisingly image of the structure. It's roof level. This project is the Exhibition Center in León by French architect Dominique Perrol, and proposed a bidirectional grid of triangulated trusses working in both directions to cover a large space, exhibition space of around 220 meters by 50 meters. This bidirectional grid of triangulated trusses is supported in the perimeter facade in several interior cores, support cores that were strategically disposed in order to control the maximum span in the longitudinal sense. So we avoid we increase the behavior in both directions. These triangulated trusses were considered with varying height. You can see here an image showing different elevation of these triangulated trusses. Since it has a bidirectional behavior, to understand this varying height, we need to see it spatially. Because, otherwise, we don't understand why it is varying the height of the truss. And of course, here we will have it will be supported by the transverse trusses and so on. The purpose of considering this bidirectional grid was that since it was covering a very large space, the usual way of working with the steel structures will be to choose a main direction where we have like the main beam of the main trusses and a secondary direction with perpendicular transverse secondary beams that will span between main trusses. This is the common way of working with the steel structures. Since the steel structures, either they are columns, beams, or trusses, they are linear elements. So we propose a linear configuration. In this case, however, since we were covering a very large space, there was the architectural intention to have some grid in this structure, not to have a very monotone, continuous structure with similar trusses that will repeat every 10 meters or so. So, of course, in terms of construction, this solution is much more complex. It's on all the connections they have to assure continuity of both trusses, longitudinal and transverse. So the continuity of the nodes is much complex, but it gives this idea, this image more like a surface, not like a parallel structure, more like a continuous surface that serves as the roof of this space. We can see in this construction image inside and on the finished building. Interior from the exterior. A similar process or a similar thought came in this project. It's also a roof structure, in this case with the extension of the Euskalduna Congress Center in Spain. This was the original building, and this is the extension. This was done by architect Federico Soriano and is located in Bilbao. And the main element, as I mentioned, was the roof that had to cover an irregular geometry in plan, since it has to adapt it to the available space in what was before a plaza near the entrance of the Congress Center. From the very beginning, the architect wanted a structure that avoids to choose a main direction. Since we were covering an irregular surface, he didn't feel like having like a main direction, which, as I mentioned, will be the more common solution for covering this space, which have a maximum span of around 50 meters, 45 meters. So he came with several proposals that were by superposition of circular, rectangular, or square shapes, one over the other, which cover an irregular surface quite naturally without marking say the one direction. We started working on this idea, but we came with the problem that the structural elements require a very high rigidity, both in bending and in torsion. So it required big sizing of the elements, and it didn't work properly. However, this configuration also suggested the possibility of considering an application of classical reciprocal frame structures. As you know, a reciprocal frame structure is constituted by a set of self-bearing elements arranged so they mutually support each to another in a closed circuit. So in this example, in this case, for example, we have a beam that is supported at one end. The other end is supported in another beam that has also one end support and another end supported in another beam. The final fourth beam that is supported on the initial one. This configuration can be made regular with following triangular, square, 5 side shapes, 6, etc., or can be irregular. And this irregular configuration or reciprocal frame structure could naturally adapt to this irregular surface over the and serving as a roof structure, and maintaining this architectural idea of irregularity and adaptability to the site geometry. So the architect liked the idea, and we worked together in developing this geometry. As you can see, it follows this principle of one beam that is supported in another one in a closed circuit. Here we mix very different spans and orientation, so it's clearly irregular. And in the case of regular reciprocal frame structure, it's very intuitive to know how it works because they are simply supported beams. But when it becomes an irregular configuration, and as this is the case, it's non-intuitive at all, because the rigidity depends not only on the span, but also on the rigidity of the element. So what we did to try to control somehow, or to have an understanding of the behavior of the structure, was in a very simple linear model, place different punctual loads and observe which was the shear paths, the load paths. So that gives us a kind of control or understanding of the structural behavior. Also, we played with that since in some areas it was required to control the height of the elements, because it was the communication of the new extension with the original building. So in that cases, we could increase the number of elements and we could reduce their size. And by reducing their size, the load path moves to other areas where the elements were more rigid. So it was a structure where we could quite easily play if we wanted to reduce the size of an element or increase the size of another. And this was the final configuration. As you see, there's a mixture of that varies from small high profiles to large spatial truss beams. And actually, in some cases, there are like large beams, large trusses that are supported in smaller beams, since they save a smaller span. And this configuration on different sizing of the element increases this idea of irregularity that the architect was searching. This is an image during construction. Of course, it has temporary proppings because this is a self-supported structure that requires the complete set, the reciprocal frame structure to be totally built, because otherwise you don't have the closed circuit. So you require temporary proppings until the structure is completely finished. These structures have a problem, let's say, is that they are very deformable, because since one beam is supported in another, you increase the deflection, you add the deflection from one wing to the other, etc. In this case, since it was a roof level and the main loads were permanent loads, we could control that with counter elevation. But for a floor deck or other uses, could be more complex solution. This is the final building and the image from the interior. As far as I know, is the largest reciprocal frame structure built in the world, especially because it's not usual to do this kind of thing at large scale, also due to these requirements of deflection control. CaixaForum Madrid is a very well-known project in Madrid by Swiss architects Herzog and De Meuron, and it's probably one of the most complex projects, or at least building projects, in which I was involved. I worked in this project in collaboration with Swiss Swiss engineer Heinrich Schnetzer. It was a refurbishment of an existing electric plant in Madrid, and the architectural concept, the architectural idea was very strong and was a real challenge in terms of the structure, since they proposed to cut off the lower part of the existing brick facade and to create a covered square, a plaza, underneath the existing building that will ideally be suspended without supports. Then the program was completed with a basement and with an additional upper level and roof level. The structural challenge was really impressive, but also everyone in the team, starting from the architects, they were really conscious of this challenge. So all the design, all the development of the project was focusing on how to structurally solve in the more convenient way, in the more natural way, this challenge of suspending the existing brick building. This image shows the structural concept, which is actually quite simple. There are three main supports, which are communication cores, both for services and elevators and stairs, and a perimeter wall with two large concrete wall beams inside also. And all this superstructure supports all the gravity loads from the building. Then the upper floor level, which are exhibition levels, have a quite clear space of around 20 meters by 30 meters for exhibition. That was solved with a composite floor deck with the steel beams and a composite floor deck, and then the roof level solved with the steel structure. These three concrete cores we solved with reinforced concrete, and they were finished with a glass mirror cladding. So you somehow you see through the glass, and then you come to a black painted concrete, and somehow it reflects, so you don't really feel like a massive core. And this wall is a post-tension concrete wall, which was connected to the existing brick facade, existing brick wall. This is an elevation showing the post-tension concrete. Yeah, after several considerations, it was decided to do a linear horizontal tracing for the cables. just an image of the behavior of this macrostructure controlling the tension and the compressions on the different areas. Okay. I can. Okay. So this is an image of the construction. We have behind the brick facade, the brick wall. These are the post-tensioning cable, the reinforcement of the concrete facade. One of the challenges, or one which we thought a lot about it, was how to connect this post-tension concrete wall to the existing brick wall, which was around 1 meter thick. At the beginning, we thought it would be better to connect it after post-tensioning. So we didn't introduce post-tension efforts on the brick facade, that we didn't know how it will behave. But then it was very difficult to do this connection afterwards, once we have the cables in tension. See, we have a 1 meter thick brick facade. And also there was a thought is that after connecting the two elements, brick facade and concrete wall, they have to work together. They will be joined together for the rest of their life. So I thought was since they will be connected and they have to work together and transfer efforts, the better it will be better to start to connect it from the very beginning. So this is a section showing the brick wall and the concrete wall that was connected with several concrete corbels that goes inside into the brick facade, and several connections just to try to avoid not to concentrate all the loss on these corbels. Also, the post-tension cables were located eccentrically from the concrete wall, so they will introduce kind of compression in the brick walls, not to have a major eccentricity on it, but somehow this is kind of theoretical, I think. And this is an image of the post-tension through the brick facade, and a picture of once it was post-tension, we retired the temporary propping. An interesting thought about this structure is that by this gesture of cutting off the lower part of the original brick wall, it transformed radically the conception of the building, and what was initially a structural brick wall was then transformed in a covering of the post-tension concrete wall in the new building. Folding structures. For more than 20 years, Spanish architect Sancho Madridejos has developed a number of very interesting projects in what they call folding structures. By folding, what they want is to create new spaces and new structural configurations that work by form. This is by the process of transformation, a flat surface, a plane that will work by bending. By folding it, we can create a configuration that will reduce the bending efforts and work mainly in axial efforts, either in tension or compression. It's the same transformation process by which a linear beam that works in bending can be transformed into an arch that work under compression forces, or into a hanging cable that work under tension forces. This is a small project of a chapel in Spain, different views, model, and an image showing how the main efforts are axial efforts, while bending efforts are limited, which allows to reduce the size of in this case, of the concrete elements, and a couple of images of the finished building. And another interesting project, the Center of Arts and Technology in Segovia, which is impressive, the conical dome in the entrance. That required, however, a very complex construction, especially in terms of scaffolding. This project actually was developed by Professor Jorge Conde, while I collaborated in the site supervision. Also with Sancho Madridejos is this project, in this case with the steel structure, Álvaro Cultural Club in El Cairo, which is a small structure for an stage, an outside stage in a plaza. And they propose a quite complex geometry also, in this search of folding and in looking for configurations that work by form. The geometry is formed by a double scheme with that combines an spherical geometry for the inner surface and a toroidal geometry for the exterior surface. And this double scheme supports the roof level where it hangs the lighting and the requirements for the stage. That combines also a double geometry, an elliptical Vieren del truss, and a circular spatial triangulated truss. The result is also a configuration where axial efforts are predominant with none or very limited bending, and the purpose was to design the elements are as small as possible with the smaller size as possible. By this, the different elements were sized according to the efforts they had to support, axial efforts. And in some areas where the efforts concentrated, the grid was double. So we increased the number of elements instead of increasing the size of the elements. And after several attempts, it was decided to choose an X profile type for the elements, in where there is a main steel plate that has the capacity for transferring the whole loads, the whole axial efforts, while a secondary steel plate is disposed perpendicularly to prevent buckling of the main steel plates. In this case, the secondary elements can therefore be interrupted in the nodes, which simplifies enormously the nodes connections that have sometimes to assure continuity of 9 different elements coming from different angles and position, and also increase the visibility of the impression of lightness, since not all the elements are continuous, only a small steel plate. And we can see it here in this detailed picture, and a couple of images of the final stage structure. You can see very clearly the nodes and the interruption of these steel plates. This is a very recent project in the south of Spain, the Faculty of Psychology in Malaga. It's a massive 3 floors building, and the main characteristic is constituted by the more than 30 courtyards that are disposed, as you see, one not one continues to the other, but in a spatial arrangement, as we can see here, in order to allow for cross views to the courtyards from one room to the other. And it was a project with that. It was very difficult to us to find which was the more convenient structure for this building. And in particular, the difficulty came because of the position of the support, which was an architectural requirement. And since the supports were only located at one side of the courtyards, that makes 18 by 3 meters. So if in one side we have support, in the other we don't have support, and this for allowing this transfer view width from one room to the other in the diagonal. We made several attempts, including post-tension concrete slabs, until we finally came to this solution, which actually is quite natural because it's the same. It follows the same principle that follows the courtyard. they dispose, is formed by the steel beams, located at both sides of the courtyard longitudinally, and a transverse beams that is disposed on the side of the courtyard where we don't have a support. So it's at the end, I think it's a very natural solution, and that follows the same configuration, the same idea for the architectural configuration in plan. And then it was a composite solution connecting these steel beams with a concrete slab. And the configuration is completed with this triangulated truss in the facade that allows to solve the large cantilevers both on the front side and the rear side. Here we see some pictures of the construction. Particularity of these beams and concrete supports on the courtyards came from the fact that the concrete supports on the courtyards were located in the courtyard, inside the courtyard, so you can see them continuous in the courtyard, while the steel beams had to be inside the building, outside the courtyard, not to disrupt it. This makes that it makes that here we are. It makes that an eccentric here we are. An eccentric connection within the steel beam and the concrete support, as well as within the transverse beam. So it's kind also for reciprocal configuration, more locally in terms of this node. So we have like a steel console that support these longitudinal beams that then support these transverse beams that is located outside the courtyard. This. No. Sorry for that.
Video or something? Is there a video representation?
No. No.
No.
Only? Yes. No. No.
Don't know what's going on. Doesn't respond.
No.
And the video is false.
Oh yeah.
Maybe the internet?
No. No.
Você traz controlar o suprimento.
No.
Maybe the master version. Probably.
I was for my